Hey y'all, I'm Sunny Shell, and tonight I'll be discussing all things magnet with Dr. Ben Davis and Dr. Michael Vandegraff. So sit back, buckle up, and let's get to the sunny spot on Skeptic Haven.
Jefferson laid great stress on it. It wasn't enough, he said, to enshrine some rights in a constitution or a Bill of Rights. The people had to be educated, and they had to practice their skepticism and their education. Otherwise, we don't run the government. The government runs us.
Good evening, everyone. I'm so glad you could join us. I want to welcome Vandy back and Dr. Ben back to the show. I'm so glad you guys were able to join me tonight. So we'll start with Dr. Ben. How have you been doing?
I've been hanging in there. I've been doing pretty good, I guess.
Great. And Vandy, how about yourself?
Oh, I've been doing quite well actually. It's been a good week of work at the lab, and things are coming together, and we're like going to finish up this project. It's going to be great, and moving on to other fun projects as well.
Cool. You want to tell us anything about the project, or can you? Is it top secret?
It's not top secret. We're trying to use an array of mirrors to do imaging of an ultra cold atomic cloud from multiple angles, so that the people can crank it through their machine learning ray tracing thing and pop out a three-dimensional reconstruction of the thing, which would be awesome, because there's so many times when I'm like, I need the laser, I need it to go through this spot, and I don't know what spot it's going through, but it's not going through that spot, and I want to move it to that spot, and I have to spend 3 days twiddling a knob instead of... Sorry.
You are super excited. I love it. Now, Dr. Ben, do you have anything exciting going on in your world?
I just teach these days. So I don't get to play with lasers and ultra cold clouds, atomic clouds, or anything like that anymore. I did write a paper for the Interstellar Research Group.
Okay.
I found a name. It's just a bunch of old white guys getting together talking about interstellar travel. But yeah, I wrote a paper recently. When that gets published, I can send that to you.
That's awesome. Congratulations on that. You guys have awesome lives. I don't.
Is the paper about using lasers to do interstellar travel?
No, actually, it's kind of mundane compared to that.
I mean, the physics of that is pretty mundane. You just hit it at a thing and it goes.
I'm trying to remember the term and I can't even remember it now. It's a new idea though. Cosmophoria or cosmophorio. The idea is that maybe the reason, well, okay, you got to go back to the Fermi paradox, right? Because the Fermi paradox basically boils down to
where is everybody?
There was intelligent life, they'd already be here.
Yeah.
Right? Because if they got a 10,000 year head start on us, that's the blink of an eye in evolution of the galaxy, right? So if there's any other advanced civilization, Captain Kirk and his starship ought to be hovering over us, talking to us already. So the fact that there isn't,
as far as we know,
some real questions. It's like, are we the first? Are we alone? And if we aren't alone and we're not the first, what happened to the other guys that came before us? And so they generally refer to that as the Great Filter. Very often the example that's used is nuclear war. Every society ends up, destroying itself, when it becomes sufficiently technically advanced. There are more mundane explanations as to why that kind of thing might happen. For example, you might just run out of resources. You're expanding out. And again, the whole Fermi paradox sort of believes in colonization as your standard model, which, colonialism was a big thing 100 years ago. But, maybe when you hit a certain technological level, you don't want to colonize the whole universe anymore. Maybe you're just happy in your own neighborhood. But this argues that you might run out of some sort of resources that just want to allow you to expand beyond a certain point. And they actually use thermodynamics as the argument. It's like you run out of energy as a civilization and you just can't go any further.
Yeah, but that you'd be able to pull it off for more. That wouldn't prevent you from lasting a few 100 million years, I would think.
So my value add in this is it might be something super mundane like the soil itself. It's like,
yeah, if you can't get off the planet, yeah,
that our soil has these living organisms in it, these microbes that nitrate the soil and keep the whole cycle going. And it's not necessarily a given that we can just take some soil and transplant it to Mars and start a completely new civilization that's independent of the mother, world, and just keep going and keep growing like that. So that's the gist of it. I basically just told you my whole spoiler on the paper.
No, this sounds fascinating, actually.
No need for the paper, yeah. No, I think it's awesome. I think it's awesome. You guys, I love having y'all on, and I'm really happy to be able to highlight some of the cool things that you guys are doing. If you are in our chat and you want to ask a question of these wonderful guests, please be sure and put that in the chat, and we'll be sure and ask that. So I am going to kind of start with a cool question. We're talking about magnets today. So let me move. There we go. Now you guys can be up on top, and I'll be. Anyway, can you explain how magnets work, particularly in terms of their atomic and molecular properties?
So the short answer is no, because magnets are all black magic. Okay, sent here directly by the devil in order to make us do their bidding. But if I'm going to have to give you the NASA shill actual version of it, basically, so the thing about magnets, I think that's sort of fundamental is its relationship with electricity. Magnetism and electricity, you shouldn't really talk about one without talking about the other. And the reason for that is that magnetism is caused by changing electric fields or moving electric charges. And in some sense, one is a consequence of the other and vice versa. So what that means is that if you, like, when they first figured out that when you send electricity through a loop, that you get a magnetic field through it, that was very weird and mysterious. And then if you put these random rocks that are kind of heavy and sometimes, then it'll twist with it. So what causes magnetism fundamentally is that same effect, electricity going around in a circle, but on the atomic level. You have the electrons moving around the atom, the nucleus, and you also have sometimes the electrons sort of spinning on their own axis. And both of those are examples of little loops of current that cause a magnetic field.
Okay. Dr. Ben?
So yeah, you typically can't have a magnetic field without the presence of an electrical current. And the funny thing about magnetic fields is if your current's running like this way, right, it's running through a wire in a straight line, it makes a field that goes in a circle around that wire. Now, yeah, I did use my right hand, right?
Yeah.
So that's kind of weird. You usually don't have one field making another, and you generally don't have a field circling around another field like that. So that's kind of weird in and of itself. I'm going to add one more piece of weirdness to this, because if we get really deep in the next 50 minutes, I'm going to blow everybody's mind, because it's like one of the most fascinating things, but it takes some thought to understand what's happening here. So first fact, if you will, is you have to have moving charge to make a magnetic field, period.
Okay.
And magnetic fields, when you have them, don't do any work. Now, for a physicist, that means something. For everybody else, that may or may not mean anything. But if you pick something up in a gravitational field and you work against the gravitational field, that object gains potential energy, and you let it go, and you can release that energy by letting it go. And so you know that you've stored energy in that object by picking it up to a certain height, and you're releasing that energy when you let it go. That's typically the way fields work. And you can do that with a charge field, an electrostatic field if we want to get fancy, right? You can do that with a field that's just charged. You can pull this charge away from this, and you can do work on it. And when you let it go, you get the work back. That's exactly what voltage is. That's what electricity is kind of based on. But magnetic fields do no work. And so what that's telling you is that if you take a charge and you shoot it into this magnetic field, this magnet, if you will, that has this magnetic field around it, that charge may do all kinds of crazy loop-de-laws and all kinds of things around that field. But when it comes back out and leaves that magnetic field, it has exactly the same kinetic energy it had when it entered it.
Okay.
Nothing else behaves that way. And there's a very good reason why nothing else behaves that way. But I'm not going to tell you yet.
Darn.
I don't know the answer to this, by the way. So I don't know exactly what he's getting up to, and it's going to be everything about what I'm doing to figure that out.
It's quite. I'm looking at the other questions I have for you, and now I'm like, oh my goodness. Okay.
Well, see, that's why I didn't want to go too far with it, because it's like, if you just want to talk about how permanent magnets work, then that's aligning magnetic domains and the spin of the electrons all working together. And
yeah, this is sort of, yeah.
You know, and if that's the kind of thing we want to have a discussion about, or why they stick to the refrigerator when you stick them to the refrigerator, then we can have that discussion on that level. So I don't want to, you know, I don't want to go way off here to Alpha Centauri if most people just want to know how to get into orbit, right?
Right. So I want to know all the way out there, but we'll start slow. We'll just kind of gradually ease our way up. Some of the other questions that I have are, how do magnets generate a magnetic field? Which I think you guys kind of already answered that maybe, but let's maybe focus in on that a little bit.
Okay.
Yeah. So basically, atoms, certain material, for one thing, there are a lot of different ways that a magnet or a substance can produce a magnetic field without without making like an electromagnet. But typically, basically what's going on is that you've got an atom and it's got electrons and stuff that are moving around and that are spinning and stuff like that. And each little itty bitty atom is itself a very weak little magnet. And you get a lot of them. And because of the way the math works and the physics works, it is in some circumstances energetically favorable for them to line up together. And when they all line up together, then all of those little magnets are adding together to act like a big magnet.
Mm-hmm.
And that, but it happens more with certain atoms than with other atoms. The like classical three magnetic sort of metals originally were like iron, nickel, and cobalt. Nowadays, you've got some of these like rare earth things that are crazy because I don't know what you put the right like atoms against each other and whatnot, and then you have a few of the atoms just like have a like crazy baller electron that's just like really booking it or something. I don't know, and that's how you get like these like crazy rare earth magnets that are really powerful compared to like just a magnetized hunk of iron.
Yeah, modern day ceramic magnets really are the work of the devil. You know, sign some sort of contract, you know, in blood, you know, with Satan himself to figure out how to do that.
I feel so validated right now because people always troll me about magnetism. Magnetism is a topic you can fall into. You can just fall into that hole. And
we're gonna fall into the hole.
Yeah, we're falling. Yeah.
But okay,
I say that about angular momentum too, and angular momentum is one of the subholes that you fall into when you fall into the magnetism hole.
Well,
so
looks like
if you want the pragmatic answer, you start with the piece of iron, right? Iron, nickel, cobalt, the magnetism triangle. You start with a piece of iron and you stick it in a coil of wire, and you run like 5,000 amps through that coil of wire. So it makes the solenoid that makes this really intense magnetic field around this iron core, and it causes all those magnetic domains to align with that magnetic field in that coil. And so you don't have to do it for long. I've actually seen them do it, manufacture magnets. It only takes a few seconds, but with enough amperage. But it makes this really intense magnetic field, and then it causes all the atoms to line up in that iron, and then you pull it out and you've got a permanent magnet. Until because this is a non-stable equilibrium, right? Until you heat it up or hit it with a hammer, run a big shock wave through it, and then that will destroy the permanent magnet. So magnets are actually kind of easy to destroy. They don't normally, want to stay in that state, that unrandomized state.
Yeah. Most of the time, it's actually energetically favorable for two domains to anti-align. And this is very obvious to anybody who's ever played with magnets. Having them align, like if you have two magnets and two north poles up here and south poles down here, and you try to just put them side by side, they repel, right? They want to flip. So, but there are other physics reasons and ways that it can sort of happen in. I guess I'm just thinking about the two-dimensional Ising model because I'm weird. But that's when you just have an array of just individual ones that are interacting with just their nearest neighbor, and you can simulate the thing. And it was solved in the 40s by some guy.
Well, first of all, let me just say that I like your kind of weird. This is the weird that gets me excited. I like this. So we actually have some questions from the chat, and so we might be going way down, and I really like that. We might be squirreling off a little bit, and I kind of dig that. So first one is from Al Trucker. In the case of ferromagnetism, which metal is the best ferromagnet?
I'd have to look it up to be sure, but it's bound to be iron. I mean, it's called ferromagnet for a reason. Ferrous is Latin for iron.
Yeah, it depends what you mean by best. Which bear is best, right? Who can tell? But most powerful, probably iron. I would think, at least of the abundant ones. When you do this, I don't know. For example, I have no idea if a chunk of neodymium is magnetic. Do you know, Dr. Ben?
Not off the top of my head. I mean, those are.
They're the things that they make in the black magic ceramic magnets. This
is where old age comes into play, right? Because I actually lived through the time that we talked about the magnetic triad, iron, nickel, and cobalt. So those are the only elements, if you'd asked me in 1985, those are the only three elements that exhibit the kind of magnetism we're talking about, the permanent magnetism. So nothing else on the periodic table has those properties. So then you can make these ceramic magnets that are really strange combinations of several different elements, neodymium being one of them, that have stronger magnetic properties. But we're talking about molecules now, and so I don't know which molecule is going to be, the strongest magnet made into the strongest magnet.
Okay.
The other thing about rare earth elements is that they're not particularly common.
Right.
So like I don't even know if it makes any sense to ask about like if you have a lump of neodymium that you just pried out of the ground, like would it be magnetic? Dr. Penn says no. I totally believe him. I have no idea.
You disagree with Dr. Ben at your own peril.
I would never.
I've been wrong, but it doesn't happen very often.
That makes one of us.
So the next question that Outrider had is,
I don't say much.
is liquid metallic hydrogen a good material to make magnetic star oceans out of?
I would expect it to be. I mean, because it's literally a single electron. And, so you should have a perfect magnetic, what's the word I'm looking for? Magnetic quantum state that you could line up, with all of those little hydrogen atoms. And of course, it would have to be cold, so you wouldn't have a lot of thermal energy, disrupting it.
Yeah, that's hard because the thing about hydrogen is it gains a lot of kinetic energy at or a lot of velocity. It's light and it moves very fast when it gets hot because temperature is kinetic energy, and when it's light, the same amount of kinetic energy moves like a lot of motion. And I don't know if that scrambles it.
So, I got curious about the iron question and what the best magnet is. Is there some way I can share my screen on here, or would I need to
There is, I think, Wes maybe in the back, he might be able to help.
Yeah, he said yes in the private chat. So, how do we do it? Present.
Do the present button next to leave studio.
Let's see. Give me a second. I'm going to do this. All right. So I am presenting. Share screen. I'm all excited now. Share.
It took you 23 minutes.
All right, then I will add you. There you go.
All right. So if we look at the periodic table, this is interesting to me, and I do not have an answer here. So if somebody else has got one, I sure am happy to listen to it. Iron, nickel, and cobalt are right here on the periodic table. That is pretty wild as far as my understanding of this, because these are, if you quick lesson in the periodic table, this is when a shell closes up when you move into a new group, right? So you're in the middle of an open shell. So you have, or at least an open subshell, right? So you have basically, in all three of these cases, you have 3 holes, if you want to look at it that way, or about 5 electrons running around in this outer orbit. And they all have to align for it to have a reasonable magnetic moment to it. So I'm not quite sure how that works. Suddenly that's giving me a whole new thing to study and think about.
Black magic. It's black magic. That's how it works.
Yeah. I mean, what I was expecting when we talked about what the best magnet would be is I was expecting something over here, which has 1 electron in that outer shell. And so it would be real easy to make that spinning electron sort of go in one direction with all its neighbors. But that's not where your good magnets are.
Yeah, no, they're not. And that is actually the magnetic behavior of specifically potassium and rubidium in that first column. And now strontium. I work with strontium, not potassium or rubidium. But those are the atoms that rubidium was one of the first atoms that was able to be laser cooled and stuff, and you can get it down to crazy low temperatures. So each individual atom is only moving 10 centimeters per second, which is really slow. And then the magnetic properties of the individual magnets becomes a tool that you can use to trap them, because certain magnets do not like being in electric fields because that sort of squishes them and makes them be higher energy. And nature just wants to be really lazy and just distribute all of the energy down.
You see, rubidium's right there on the edge of the periodic table.
Yeah.
It's right here.
Yeah, and now we use strontium, which is right next to it.
Right. So these make perfect sense why they would be magnetic.
Well,
right?
But strontium in its ground state is completely non-magnetic.
Absolutely.
because it's got those two electrons that cancel each other out. That shell is filled up.
We need to remember one other thing though when we have this discussion is we're talking about permanent magnets, right?
Yeah.
How they behave when you put them in a oscillating magnetic field, or how they react to the presence of an external magnetic field.
Totally different.
Because they re-randomize and don't become permanent magnets doesn't mean they don't have some really cool magnetic properties.
In
the presence of another magnetic field.
Yeah, that I remember the point that really drove that home to me, like how sensitive those sorts of systems can be. Just like a cloud of atoms to magnetic fields. The Navy sent some people like through the universities and stuff, and they visited our lab, and they were like, the reason we're visiting your lab is because we're thinking about building an ultra cold atom system to put in airplanes that we can use to detect magnetic fields very sensitively, so that we can use these ultra cold atoms on the airplane to detect enemy submarines at the bottom of the ocean. Which what? The systematics on that sound very difficult, let me say. But apparently it passed the smell test to get funded. So, yeah.
All right, we have another question, and this is from Titan Uranus. Question for Dr. Tapioca Weasel. Are planets magnetic? Follow-up is Uranus magnetic?
Well, it was until I tightened it, okay? Planets is Earth. Earth has a strong, important, culturally significant, and useful permanent, for some definition of permanent, magnetic dipole moment. Other planets do as well, but not all. They don't all have substantial ones. I don't know if Mercury does. I don't know if Venus does. I don't know if Mars does. I know Jupiter does, but it's like getting like weaker. And I don't know about some of the other planets.
Typically, the smaller the planet, the less likely it has a magnetic field.
Okay.
Yeah. And why is that?
Yeah, I was just going to ask that question.
Now we get to go back to my astronomy. And so, now we're more in a comfort zone, right? The idea of the Earth having a magnetic field is that it has this molten core of iron and nickel that's circulating. And so that circulating plasma is not the right word, but that circulating magma, superheated magma in the Earth's core that's spinning around is like a generator generating a magnetic field around it. Now, Mars, for example, and good things happen because of that magnetic field, right? The Van Allen belts develop, and a lot of radiation from space doesn't make it to the temperate zones of the planet, and so life can evolve on it. Mars, for example, has lost all of its plate tectonics and presumably is frozen solid all the way down to the core. And it doesn't have a magnetic field anymore because of that. It's just a chunk of metal at its heart, and it's lost its magnetic field, and it's also lost its atmosphere for the most part. So it becomes a fun conversation when we talk about terraforming Mars, because there's some very basic things that we take for granted on this planet that Mars doesn't have. One of which is a magnetic field and the Van Allen belts that shield you from the radiation. And the other thing is the atmosphere, because the atmosphere, the gravity of the planet is not quite strong enough to hold the atmosphere in place, and it's leaked off into space over time. And again, it's the fact that it didn't have the same amount of thermal mass that the Earth did, that both of those things have happened.
How much do we know about Venus when it comes to, well, one, we can presumably detect fairly well any external magnetic field, but two, what do we know about the geomagnetic dynamo or lack thereof in Venus? Because it's only a little bit smaller than Earth.
That's correct. Venus is a lot closer to Earth size, and it's definitely got an atmosphere. So, and it's never cooled down.
Yeah, it's a much denser atmosphere. And no, it's hotter than Earth.
If I cheat and ask Google, does Venus have a magnetic field?
Venus doesn't rotate very fast, though. It has a very low angular momentum, doesn't it?
I'm sorry, what? Yes, it does. It's almost in tidal lock with its yearly rotation around the sun.
That might be the reason. Because if it's almost in tidal lock, the thing that's going to get the most tidal slowdown is going to be the goopy bits in the middle that would cause a magnetic field. So
is that a scientific term? Goopy
yeah,
bits?
the goopy bits. Yeah.
Yep.
So tidal locking refers to the phenomena where if you have like a sun, a star, and then you have stuff that's orbiting it, eventually after a long enough period of time, one side of that planet that's orbiting it, one side is always going to be facing the sun, and one side is always going to be facing the way. This is what has happened with our moon. Our moon always has the same side facing us, and it's just sort of like wiggling. The reason for that is that the tidal force will cause an object to sort of bulge out a little bit. Mm-hmm. And then if you just look at you can just think of the math and be like, okay, it's like a sphere, but with a big weight on this end and a big weight on the back end. And the effect of gravity each little time, a little bit, is to sort of slow the rotation when it's going away, and it slowly slows it down, and eventually you get locked, and then you just sort of settle in. And there's a whole. I might have taken this work. Crap.
It's not exactly magnetism related, but I was shocked the first time I ever saw the far side of the moon, because
my grandpa has my grandpa has a crater named after him on the far side of the moon.
That's not surprising. But when you look at the face of the moon, you know, the one that's always facing the Earth, the one you always see when you look up at the moon, there's all these dark spots, all these craters. When you look at the backside of the moon,
very different
probes to take pictures, there's no dark craters on the backside of the moon. And it's because all of this lava, when the moon got in tidal lock with the Earth, all of this lava flowed out of those craters and filled them in and made them dark in appearance. And that doesn't happen on the far side of the moon. So it's literally that dense rock coming up to the face of the moon, the side that faces the Earth, that has caused that tidal lock. So again, nothing to do with magnetism. I got to read this. This is from NASA, right? So I'm assuming it can be trusted.
NASA shoe?
Even though Venus is similar in size to Earth and has a similar sized iron core, the planet does not have its own internally generated magnetic field. Instead, Venus has what is known as an induced magnetic field. This weak magnetic field is created by the interaction of the sun's magnetic field and the planet's outer atmosphere. So it doesn't generate its own magnetic field, but like iron, in the presence of the sun's magnetic field, some of its atmosphere actually polarizes the other way and tries to cancel out the sun's magnetic field.
Okay.
That's induced magnetism. That's the fancy way of saying this magnet caused this other magnet to form.
Yeah. So wait, hold on. So Venus is like really strongly diamagnetic, right? Or basically, or not really strongly, but a little bit.
Let's say a little bit. And you used the
Is
term
it enough?
diamagnetic, so you better define it now.
No. Diamagnetism. Diamagnetism is the thing that people confuse for superconductivity and then publish papers about LK99. Diamagnetism. I'm not wrong. Diamagnetism is a phenomenon a ferromagnetic material like iron is a material that if you hold another magnet up to it, it'll attract to it. I think if I'm wrong about this is really embarrassing. I think diamagnetism, instead of it being attracted to it, it's repelled from it. Just like generically. That might be paramagnetism, though. That might be paramagnetism.
I hate to always go back to Google for all this stuff.
Well, I feel better about that.
Paramagnetic versus diamagnetic. If it has it has to do with how it's configured in the periodic table. So this sort of goes to some of that discussion we had earlier. If it has unpaired electrons, then the substance is paramagnetic. And if all electrons are paired, the substance is diamagnetic.
Oh, so it's neither.
Yes, but the difference is that it's not going to be as strong of a magnet, and it's probably going to be a lot harder, even if it's a solid, to make a permanent magnet out of it. If it's not diamagnetic.
Well, my point was more that if you have a magnet.
No, paramagnetic.
A big old bar magnet, and you bring it towards a non-magnetized piece of steel, but or non-magnetized piece of iron rather, because it depends on the steel, I guess. Even though the iron is not magnetized, unless you've done other stuff to it, it will still be attracted. Like you will induce some magnetism, and the effect will be that the object goes towards, and it's a high magnetic field seeking system. Whereas I thought that a diamagnet was. Yeah, we do a whole show about magnets, so we don't even know like what a diamagnetism is.
It's one of those things we learn. It's one of those things we learn when we're like at the sophomore level in college, and then it's like we never use it again and we forget it, right?
Yeah, right. Yeah.
So
when I talk about
what you're saying is correct. Diamagnetic materials have a weak negative susceptibility to magnetic fields and are slightly repelled by magnetic
I feel
fields.
so smart right now. Oh, this is why I went into physics, people.
Have a small positive susceptibility to magnetic fields. Now we have to talk about what susceptibility is, right?
Yeah, so susceptibility
it's how quickly
magnetic a thing comes.
It's how readily it's affected by a magnetic field. If it has low susceptibility, it's not going to change its internal magnetic field very quickly if you bring a magnet up to it.
It is a very well-named property. Magnetic susceptibility you couldn't think of a better name for it. It's how susceptible it is to be magnet-like.
And ferromagnetic materials, iron, have large positive susceptibility to an external magnetic field, and they exhibit a strong attraction to magnetic fields that are able to retain their magnetic properties after an external field has been removed. So ferromagnetic is the magnet that retains its properties. The others are reactive in the presence of another magnetic field. And one actually lines up with it and one actually opposes it, which is really interesting. And again, you could spend a lot of time just trying to figure out why that is, but that goes to the structure of the atoms you're talking about and how those individual electrons react when they see a magnetic field.
And like very importantly, perhaps even more importantly than the structure of like the individual atoms, is the structure of the whole solid state system or the whole condensed matter system, when you've got all of these atoms aligned together in some sort of arrangement, and how the electron sort of, because when you have that, you don't really for certain materials like shiny metals that are conductive, the electrons can just kind of like move along, and they don't really belong to any particular atom. The outer electrons do. Whereas and that of course can lead to all sorts of weird funky effects that are like emergent phenomena that you don't get from the bare atomic physics until you get a lot of them, because more is different. And that's like a very important like thing to appreciate about nature.
Everything's way more complicated than you think it is.
Yeah. Yes.
Okay, we have a few more. Y'all are making my job so easy. I could just sit here and I don't have to do anything but just look at you, and it's pretty cool. But I do want to get through a few more questions from the chat, and then I really want to dive into the little teaser that you had at the beginning, Dr. Ben.
Oh yeah.
Okay.
Oh yeah.
So,
we don't want to forget that.
Yeah, no, we don't. So let's see. Al Trekker asked, how does a temporary induced magnet work where you use a ferromagnet to stroke magnetism into another metallic object?
I'm sorry, I was looking to see if I had any like good rare earth magnets, because I could do this. I could do it with some paper clips live on, like it would take 2 minutes if I had a good magnet, but I don't know if I have one.
Are you taking this one or am I?
I'll take this one because you basically took it earlier. So I'll give my sort of version of it. So this is very similar to, in some sense, how they make permanent magnets, because you are making a permanent magnet. And the way that you do it, that you would have maybe done in science class in school, I remember doing it in like 4th grade. If you just take a piece of magnetic substance, like a paper clip, and you just rub you just take a magnet and go whoop, and then wipe it, and you just sort of keep on doing that. Every time you do that, you're jostling a few more of the atoms so that they all line up again. And that's that's sort of similar to how Dr. Ben was explaining how they make permanent magnets, like industrially, which basically they put a chunk of thing and then they just like use coils and stuff, and they just jack up the magnetic field like crazy strong. But you going and doing it repeatedly, I think it probably also helps if you like hit it, like rub it like maybe a little bit. I don't know. That might be nonsense though.
Yeah, I don't think hitting it would help.
I guess it would hurt it.
If it did.
I was kind of wondering, like, if is it better to have a hot material above the Curie temperature and then cool it down past through the Curie temperature in the presence of a magnetic field? Would that make a better magnet than exposing just cold material to the same field?
It might. That might actually, if you pass through that temperature while you've got it magnetized, that might actually do some good. I'm not sure. We'd have to try it.
Yeah,
the Curie experiment.
We would do
the Curie temperature is the temperature that like a magnet, a permanent magnet, would have to heat up before it loses all its magnetism, because they all get. It's
when the thermal energy is so much that it just can't align itself. It keeps getting re-randomized by just the thermal energy in the molecules.
That is so great. All right. Titan Uranus asked, is it true that if you balance your chakras, you can change, oh, I can't even read it. You can change your quantum vibration frequency and stick to a refrigerator? Please tell me this is true.
This kind of makes me sad, because I'm afraid what he's telling us is that we're using so much of what sounds like double talk to him that we're sounding like some of these ESP assholes.
Allow
you
me
have
to assuage your fears. Allow me to assuage your fears. Titan Uranus is not an unintelligent Titan or Uranus or whatever.
Yeah, I heard Titan Uranus and I zoned out there for a second.
And well, yeah, I mean, that's what the kegels are for, right? You just gotta. Anyway,
Sure.
The thing about Titan is, he hates me, and the way he manifests his hatred for me is by constantly asking me to explain how magnets work. And magnets, man, how do they work? I don't know. Okay, I got as much clue as ICP does. I got the little current loop thing, and I bet they could Google it themselves. So Titan just comes in here, and it's all like, oh, I have a wrench everywhere. I'm a mod on everybody's channel. I'm just going to give Tapioca Weasel a stroke. And you know what? I listen to it, and I come back to him, and I say, thank you, sir, may I have another? I don't know what's wrong.
Well, I don't know, man. If Titan Uranus is giving Tapioca Weasel a stroke, I don't know if I want to watch that or not. I mean, I don't judge, but I don't know that I need to be here for that either.
It took me a moment to get that.
Breathe.
No, I sent. So Titan and I are in many Discords together and talk on Discord, and I sent him the link to this show, like on Sunday or something. I don't remember. And I was like, I'm doing this for you, Titan, because the whole joke, the whole joke is that I, Dr. Tapioca Weasel, am a fake physicist because I refuse to explain how magnets work and like to imply that they are dark magic or perhaps demonic entities that have seeped into our realm. And yet, I mean, describe ceramic magnets again for the chat, would you, Dr. Ben?
Me, I said that it was, some sort of black voodoo involving
exactly
selling your soul to Satan.
Exactly. And I felt so vindicated when you said that. And because they be in here being like, oh, but
it's super esoteric, right? It's right in there with the superconductors that that don't lose their properties until like minus 100 degrees. I mean, how they ever got that effect up that high, and they're all weird ceramics, weird combinations.
Yeah. Oh, those are cuprates, something cuprate. That's all I know.
Right. It's sorcery, man. It's unless you're in the field and you're doing the work, you don't understand exactly how that stuff comes together.
It's sorcery for a lot of them too. Trust me.
All right, I'm going to give him one more question before we go into Dr. Ben's teaser. And he actually says, okay, serious question. Okay?
Okay.
I read years ago that Earth's field was actually very weak, but just very large. Is that true? Now, that's a great question.
That is a good question.
Yes, so how are we going to answer it?
You're the astronomy person, so,
Well, I mean, I could sit here and go, well, everything's relative, and what do you mean by weak? And but
well, that's what I would do. It's Titan. He can take it.
I think it's actually fairly strong.
Yeah, it's not that weak. Half the Gauss.
Yeah.
Sorry.
Yeah, I mean, in terms of how nothing man-made, what actually occurs in nature, it's actually fairly strong. And if you were to go deep into the earth, you probably find that it was much stronger. On the surface, it doesn't seem all that strong, but it's strong enough that compasses work, right?
Yeah, exactly. And have worked right and reliably for thousands of years. This is not new technology. Compasses.
Yeah. So, the very large thing, it's like, this is a continuum, right? It's like an electric field. It never goes away completely. It just sort of diminishes the further away you get. So, or gravity, right? And so it's never, weak, strong, close, far. I mean, that's all tied together, and it's all sort of, it's just a question of where you're standing and what you think of as strong, right? But I think the Earth's magnetic field is actually reasonably strong, at the surface.
Yeah, it depends. It depends on what you mean by strong. If you just have a magnet on your sitting on your table, is it going to move? No. If you put that magnet in a little dish that floats and you put it in water, is it going to move? Yes. So it's not exactly hard to make a thing that you can observe it just like directly and immediately.
Yeah.
It's about, so the unit that I use, this is not actually the standard international unit, which is the Tesla, but I for anti-capitalism reasons, anti-capitalism reasons, and family reasons, Tesla gets too much credit. Just saying.
I can't disagree with that.
Tesla was not a physicist. Tesla was not a physicist. Tesla was an inventor and an engineer, and he was a hell of a good inventor. He really was, but he was not a physicist.
You could say the same thing about Michael Faraday too, but he
could barely do math. He was brilliant.
Yeah. He was still brilliant in his own way, and that's
exactly. We have not had. There has not been a physicist like Michael Faraday since Michael Faraday. I think the reason we say that is because Michael Faraday came up Faraday cages. Faraday's law. It's one of Maxwell's equations, and he did all of that without being sophisticated with mathematics, which is difficult.
Yeah, I mean, Maxwell had to figure out his interpretations, but he took really good notes.
Yeah, but he came up with the lines, the magnetic field lines concept, which is brilliant and amazing and wrong, but that's a different story. I forgot what I was saying.
You were talking about Tesla being overrated, and I brought up Faraday. You could make the same argument about him, and then you started talking about how great Faraday was.
Yeah, it was something about we were talking about the strength of the Earth's magnetic field. It's strong enough that people turned it into a useful tool before we know when that happened. So,
it's BC. I mean, it was strong enough to detect and know that it was there, even in the BC era.
We understood magnetism at a certain base useful level earlier than we understood electricity. Because it's not clear to me how well known it was. They probably did know this, at least some people, that static electricity, which would be a thing that any dry community with fabric would experience. They would experience static electricity. I don't know if they realized that was the same phenomenon as lightning. Probably a lot of them did, I would expect. But what do you do with that? What you do is you put a belt sander into a thing and attach a metal globe onto the top of it, and you make lightning bolts with it.
Yeah, I think Wes was hoping we talk about motors somewhere along the way. We haven't even touched
right.
Yeah, there was a bunch of questions that just got flung out because this was so much better. I do want to ask you, can you guys stay just a little bit longer, because I really want to hear, your teaser grabbed me. And so I really want to
me
know.
too.
And so
I might be boring
you
the
say
shit out
that?
of everybody else, but I'm having fun. So
You're not.
I'm loving
I'm
it.
having a great. I don't have any. I'm good to go, like arbitrarily, basically. But
So yeah, I do have students out there that are working on their labs, but yeah, they're fine.
All right. So if you will go over again, kind of your little teaser, and then give it to us.
All right, let's back up a minute, because when you talk about ferromagnetism, those are emergent effects, right? That's emergent physics. And so let's talk about the basics, right? And then you could spend the rest of your life trying to understand how the rest comes into play once you understand the basics. So one of the basic experiments in magnetism is you can take two parallel wires and you can run current through them in opposite directions. And those two parallel wires will repel from one another. Current carrying wires, right? They're carrying current. And so this is where we first measured magnetic fields, talked about magnetic fields, posited what they were and how they work. So speaking of how they work,
in like a rigorous quantitative way,
yeah, in
like
a rigorous quantitative way.
Yeah.
Yes. So first of all, let's talk about why magnetic fields do no work. I actually gave this talk at a con. Was that just last year? Yeah, it was just last July. And you know, I usually have a pretty good set of groupies. They can usually hang with me, whatever tangents I go off into, and they were all just looking at me like this. And half of them are going to sleep, and it's like it's a lot, right? But one guy actually came up after the talk was over, and he's like, I have a master's degree in physics, and when you said magnetic fields do no work, I've never heard that before. And I'm like, okay. And he's like, can you explain, you know, why? And it's like, I should have been able to, but, you know, it's like I'm at the end of a presentation. The next presenter is coming in, and he's breathing down my neck to get away from the table so that he can set up and get his slides going. And it's like, that's just the way it is. I mean, you know, go read a physics book, you know, which is not the answer I want to give, right?
That's what I'm doing.
Gotcha. But there's a really simple explanation as to why. When you pass that moving charge through a magnetic field, say the charge is going this way, the magnetic field is going this way. I'm doing the right-hand rule.
Right-hand rule. Woo!
So the charge is moving this way, the magnetic field is moving this way, and the force that it feels is going in the direction of my thumb. So the force exerted by the magnetic field on the moving charge is always perpendicular to the direction it's moving, which means that it can't speed it up or slow it down, which means that it can't do any work on that charge. It's only changing its direction. That's the short answer. Now, next level.
I was just going to say, this is an example of the magnetic field that is produced by a current carrying wire, and somebody is doing the right-hand rule thing. So,
now, next level. When they first started talking about special relativity, we don't have to talk about gravity, fortunately, just special relativity, right? Relativity of moving things. They realized that Maxwell's equations didn't have to be altered to fit relativity.
they explained it.
Other forms of physics had to be altered to correct for special relativity under cases of high speed and things like that, but not Maxwell's equations. That means that Maxwell's equations work no matter what inertial frame you're in, whether you're going at near the speed of light or whether you're sitting still. And it means one other thing. It means you can take the most complicated, it's got to be a real thing, right? But you can take the most complicated electromagnetic field that you can find with the magnetic field going this way and the electric field going this way and maybe even wrapping around each other, which they tend to do. But you can find a frame of reference and relativity where it's a pure electric field.
Yeah.
And you can explain the motion of that charge just like it's sitting in an electric field without any magnetic effects at all. And then you can, of course, change a different frame, and you can watch it curve around the magnetic field when you're looking at it from a different point of view or whatever. So all that tells you that in reality, magnetic fields do not exist. They are a emergent property of moving charge and relativity.
Yeah.
Wow.
If you do the calculation with the two current carrying wires, by the way, I found in my textbook it totally says it. For the record, it says magnetic forces do no work.
Hold on,
See?
let me make you big. Hold on. Let me see.
Thank you, Griffiths.
Griffiths is the shit, man. I've got him.
Right?
He's right here for me too,
Bro, I've had this copy of Griffiths for so long that this is the 3rd edition, which is I'm old. They have a 5th edition now. I need to get it, but it doesn't have the cover anymore.
Yeah, this was from my grad school years. Actually, this was from my first year teaching. I taught out of this book. So this one's the 2nd edition. But all of this, see, and the funny thing about it, this will blow your mind, is all of this is stuff that people understood in, let's say, not the mid 1800s, but the mid to late 1800s.
Yeah, and
the physics. This is stuff we figured out a long time ago.
And the special relativity stuff, like most of the mind-blowing things about like how that like sorts out all the electrodynamic stuff, that was like the impetus for special relativity. Like it was like the very first thing that was like really like, oh, this just works in this theory. It just works beautifully. And one manifestation of that, and I might get some of the details wrong, so Dr. Ben or whoever, feel free to correct me. If you do the calculation with the two wires that are carrying a current, and you transform into the frame where the current is moving, you get a length contraction effect, which basically means that instead of it being a magnetic thing that's attracting a magnetic thing but somehow not doing work, it's instead both of those wires become slightly differently like charged. And because they're differently charged, or similarly charged depending on the direction of the thing and therefore the magnitude of the shift, you get just a straight up repulsion, because now instead of being neutral with a current going through them, they're charged but with no current going through them. I think that's one of the ways in which that manifests.
Yeah, you guys have created a monster now that you've shown me how to present.
Okay.
So let me try to explain this to you. Think of this poorly drawn picture, because I had to draw it manually. Think of this poorly drawn picture as two current carrying wires. And if you think about the positive charge flowing through this wire, and you think about the positive charge flowing through that wire in the opposite direction,
yeah,
then I've highlighted it in red, although red obviously was a good choice of color because it's kind of hard to see. But you actually shrink the charge distribution in the wire for the positive charges, which means they're a little more closer together and generate a slightly stronger electric field than the negative charges going in the opposite direction. And it repels them like two just static charges repelling each other. And it's a completely relativistic effect.
This is the power of a theory in physics to unify explanations for phenomena that I think is by far most beautifully and clearly elucidated through the development of the theory of electromagnetism. Because electricity, sparks, lightning, the smell of ozone in the air, and magnetism, these random rocks that would attract each other, and the fact that certain rocks, if you float them on a thing oriented a certain way, and that lines up with the stars, that's crazy and like amazing and utterly mysterious. Until basically, as far as I know, and maybe I'm not knowing about the history of physics well enough, but basically that's all kind of confusing and not really understood until people like, I think, like Benjamin Franklin like did some of the early work and like did the thing where he flew a kite in a thunderstorm and nearly zapped himself to death because he hung a key on it and did the thing. And he's like, you know what? If I just add this extra substance charge, and there's 2 flavors of it, and they go and they do this, that explains everything that I've seen, which it did.
He actually, I mean, it's one of the things that I love to talk about, which doesn't generally have anything to do with magnetism, but he connected the idea of static electricity and lightning and flow of current. And so he basically invented the lightning rod, and he has saved untold lives because he invented the lightning rod. Before he came along, people thought that that lightning was just God's wrath coming down on this random person because I don't know, it said goddamn or something at the wrong time and pissed God off. Who the fuck knows? But he starts having people put up lightning rods all over town and grounding them, you know, from the tops of the building to the ground, and suddenly there's untold thousands of people that aren't dying from lightning strikes as early as, I don't know, 1800s, early 1800s. And you know, that's I bring up several scientists that have done something like that, and they have you think the bad guys are winning, you know, but they're not. There are literally scientists out there. Norm Borlaug, perfect example. Literally scientists out there that have saved 1 billion lives. And so no dictator comes close to that as far as the lives he took. So progress is real. It only takes one guy or gal. I mean, I'm not trying to be sexist here. Just figuring out this thing and applying it the right way. Norm Borlaug grew a certain type of wheat, you know, a rice that grows in the Far East, and increased the crop yield. So 1 billion people didn't starve to death because of him. You know, so science is good stuff, I guess, is what I'm really getting at there.
Yeah,
Science saves.
It is science and scientific research. And the research into like knowledge generally about the world is, I think, unquestionably by far the most productive, profitable, beneficial investment that a society can make in itself in a intermediate to long term, and most of the time also in the short term.
Yeah,
absolutely.
Absolutely. And yeah, it's hard. It can be convoluted. It can take 100 years to figure something out. But typically, when we master some new form of technology, it makes life better for everybody.
When did the Wright brothers first fly a plane? 1903.
Sounds right. It was beginning of the century.
I should know that because I live in the same state that they did that in, and it's like everywhere. But
yeah,
I don't.
I think it was 1903. I used to think for the longest time it was 1905 because I assumed that everything that was important in that sphere of things happened in 1905 because my buddy Einstein. 1903. When did we land on the moon?
1969.
69.
That's insane.
Yeah.
1903. December 17th, 1903. So it was almost 1904 when it happened.
Yeah. Stephanie, you are absolutely right. I, I see it every
First in
day,
sight.
every single day.
But but I wanted to say, so this is a soapbox that I feel a certain obligation to get on every so often. When you were talking about scientists who, saved a lot of people. So,
And I didn't even bring up nuclear power when I brought it up.
yeah, well, that also killed a lot of people too. But
Oh, now we started an argument.
no, yeah, I think it saved more than it killed.
Okay, all right. So
you and so my grandfather produced Van de Graaff generators. There were at least two different generators that were used at Oak Ridge in the late 30s and early 40s in order to they used them to measure the collisional cross section of uranium-235.
Hmm?
So yeah, my family's legacy is fairly mixed up in that. So I might be biased in favor of the nuclear argument.
I did my research in nuclear physics on a Van de Graaff particle accelerator.
Yeah.
Yeah.
they the one of the earliest things that they also were making them for, besides as research tools for nuclear physics and particle physics, was for radiation therapy. Hold on. Actually, I'm going to insist that if I can find it, share. I don't know if I can find it though, off the top of my head. Did I find it? I think I found it. There's a wonderful image, hopefully on this PowerPoint that I'm trying to open up right now, which I can't because I do not sign up for PowerPoint. There's a great picture. So I don't have the thing. There's a great picture of this tube coming out of the ceiling, and it ends, and then there's a patient on a hospital bed right underneath it, and this patient is getting the very first treatment of a 100 megavolt beam of radiation, protons or whatever, to zap their cancer tumor in the 30s.
Mm-hmm.
They were using particle accelerators to produce radiation to zap or to just produce beams of protons to zap cancer tumors. It is the main thing that Van de Graaff accelerators are built for nowadays. Their utility as a particle accelerator it's generally less than other options, but apparently, although Dr. Ben, you would probably know more, the tunability of them is very nice compared to Krakow-Fulton machines, I think, because you can sort of dial in parameters a little bit better.
I think that's probably true.
Yeah, but so these were, when you get radiation therapy, my grandfather was one of the people who invented that, but that's not the high horse I was getting on. His friend, his first graduate student, and his business partner that he started his company High Voltage Engineering Corporation with, and who outlived my grandfather by a couple decades. He wanted to use them for all sorts of great things later in life. He wanted to use these particle accelerators to create industrial scale water purification centers, because you put the water through a thing and then you zap it with radiation really hard at a certain spot and it kills all of the germs. And I mean, there's other things you have to think about. The name of that man was John G. Trump, and he was Donald Trump's uncle. And he couldn't be more different from his nephew.
His progeny, absolutely.
Yeah, and
Oh, wait,
I
is
I
he the
I
father of Mary Trump?
no. No.
Okay.
No, Mary Trump. So Mary Trump was Donald Trump's is Donald Trump's sister.
Oh, sister. I
So
was thinking it was his cousin. Sorry
I'm
about
pretty
that.
sure. So they
Okay.
share parents. No, John Trump, he was a professor also at MIT with my grandfather, but yeah, no, he yeah. But the reason I say that is just because I know that the reach and glare of Donald Trump's influence is vastly greater, at least on the around now, than any voices that are trying to keep the rest of his family that may not deserve it from getting dragged down with him. And most of them do deserve it, is the problem, because they do, like, most of them deserve it, but this guy doesn't.
Well,
So,
like one person said in the chat, it's his immediate family that are the notable ass clowns, and I would agree with that. I think other people, but this is a really good segue to my very last question for you. Does this mean that the great orange one was wrong when he said that if you just throw water on magnets, they disappear?
Well, he was wrong about every other goddamn thing he's ever said. What the hell was he right about that?
I'm sorry. Am I allowed to swear?
Yeah, yes, you can.
The fuck did you just say? That's I was unaware of this. I don't watch the news anymore because I'm busy with the internet and physics.
You just throw water on magnets and they disappear, according to him.
Is this new, or is this
get me started on Trump? I can go all night.
Yeah. Well,
I told the boss one time. It's like I watch. Annie likes to watch all these virtual reality shows from the very beginning. You know, back when they first started doing them. And I watched The Apprentice with her the first time it came on. I thought I was going to learn about management, something that might actually be apropos to my life in some way. And I looked at that guy that first night that I ever saw him on the TV, and I thought he had to be the biggest fucking douche I'd ever seen in my entire life.
And he's proving to be worse than that.
And then I go to work the next day, and my boss is talking about how savvy he is and how smart he is and what a great businessman he is. And I said to my boss, if you ever treat me the way that man treats his employees, you will not have to say to me, you're fired. I will save you the time.
Absolutely.
Was this in academia?
No, God, no, dude.
Okay, I was like,
why do you think it's a gateway scientist on it? This is physics. I couldn't get a job in physics when I got out of grad school.
Well,
I was a software developer for 12 years, and I was an engineer for another 5 years after that.
Apparently, when I got out of grad school, which was in 2022, less than 2 years ago, is when I got out of grad school, there was a huge postdoc shortage. So I just kind of got to do whatever.
Did you do the postdoc thing? Is that what you're doing?
I am still a postdoc. Yeah.
I had a drinking buddy. Now we're really going far afield, right? I had a drinking buddy who's German. I know that's a shocker. He was in his mid-40s, and he had spent his whole career doing nothing but postdocs. And I swore that I would break rocks in the back of the building before I accepted a postdoc anywhere.
No,
it's just slave labor, man. It's just a way to get you to stay there for another 2 or 3 years and pay you nothing.
No, I'm not a postdoc with my grad. So I got my PhD from the University of Colorado Boulder, and I'm a postdoc at Stanford. So
okay.
they so one, it's a pretty good gig. Two, I love the work, and three, I love the group. Jason Hogan is a fantastic person to work for anybody who happens to be like in the chat being like, hey, I'm thinking about studying atomic, molecular, and optical physics. And I don't know if this guy's it's a good group. It's a great group. Everybody's happy. It's fantastic.
I'm glad it makes you happy.
Right? Yeah.
Like, as long as you're happy, that's what matters.
Yeah, like they pay pretty well, one, because there's a shortage, and two, because they have to. Because housing here is absurd. It's absurdly expensive.
Sure.
Just insane.
Stanford, yeah, I'm sure it is.
But like I might want to work on this experiment for the rest of my life. It's a cool experiment.
Well, you're having fun, and you're making a decent salary, so that's a good thing.
Yeah.
Awesome. So we are going to wrap up, and I would love to have your final thoughts. You can have final thoughts, final statements on anything that we have talked about on this wonderful evening, where we have gone on such a journey through the woods and through tall grass, and we've had a wonderful time. I have thoroughly enjoyed this night. So, Vandy, we'll start with you. What are your final thoughts for the night?
Oh, magnetism is a topic and a phenomenon that you can spend the rest of your life investigating a small like part of it. It's really amazing. It's probably mostly not entirely magic. I can't give you much better than that. But you know, everything's magic. Like, what is anything, man? Right? So,
like if you go smoke a joint and hang out with some buddies now.
Exactly. But something I was thinking that this was only very like sort of briefly mentioned, but I would be very interested actually in coming on again and doing a show with Dr. Ben where we talk and probably mostly agree with each other about nuclear power and stuff like that.
Oh, I would love that.
See, Sunny did it, and that was 2 years ago, and that's the last time she talked to me.
That's not true. I saw you on one of these panels like 3 months ago.
You didn't call me for 2 years.
No, I'll put you guys back on again very soon. I love you guys. Y'all are awesome. All I have to do is, like I said, I just sit here and I look and I laugh and I listen and learn. All the elves, they're great. All right, Dr. Ben.
Oh, I wanted to say one more thing. Sorry, I just wanted to say or ask one more thing rather. Is it possible to like do these things like not on Thursdays? Because the time slot, it can be difficult. Like, is there a weekend show?
So we do have weekend shows, and I'm going to talk a little bit about them in just a minute. But my show is the kind of the science one. However, what we could do, if you wanted to, is do like a pre-record and then show it on a Thursday. We could do that at some point.
It seems like a perfectly reasonable compromise.
Yeah, and who knows? Maybe we might just throw in a weekend show at some point. You just never know. Just because it's you. Just because you're a NASA shill. Dr. Ben, your final thoughts.
Final thoughts. Okay, so I have these stories that I tell that I think are only entertaining to me, but I insist on telling them anyway. And it's apropos to the whole relativity, magnetism, going into computer science because I couldn't find a job as a physicist, all of that. So years ago, I went to a job interview. Headhunter placed me a job in Columbia, which was a little bit of a commute for me. I wasn't sure I wanted the job, but I was going as a software engineer. They were hiring me as a software engineer, and I went to the interview, and it was a meat packing plant, is what the guy said. And I went in there and talked to the lady. She was super nice. She was chatty, so we had a great conversation. And she was telling me that they didn't actually pack meat. They didn't actually package meat. They made meat containers. And I'm like, meat containers? What are we talking about? Like the skin around a hot dog, or the skin around a sausage. And it's like, okay, got the picture. I said, so now I just have to ask you this, because it's a big plant, right? It's several hundred employees, and a building that's several stories tall and, covers acres of land. And I'm like, why do you need to develop a database in meat containers, meat casings? That's what they call them, meat casings. And, it's like, how many can you have, And she says, wait a minute. She goes in her back office and she comes out with 2 6-inch binders of meat casings, full of like kosher.
Binders full of meat casings.
Yeah. Kosher, latex, the stuff you cut off, before you serve the sausage, made out of cartilage, the stuff you think about that goes around the wiener skin, all of that stuff. And she's got 2 big 6-inch binders. And at that moment is when I realized that the world is a way more complex place than any of us even begin to realize. There are whole industries built around not butchering cows and packaging meat, but making the cases of the leftover meat that they grind up and put into sausages. Whole industries built around just that, and there's 105 billion people that have come before us, if you look at the math models, and everybody has tried to add their little spin to, making the world a better place. And things are way more sophisticated and way more complicated. And in the case of magnetic fields, way more well understood and modeled,
Yes.
than most people get. It's funny, I go and I give these talks and I go to these cons and we are still talking about physics that's 100+ years old.
Yeah.
That just fascinates me. It makes me wonder if we're getting dumber as time goes on. It seems like all the great things happened like in 1905, right? It's just amazing to me.
Yeah.
We're
I think there's always a handful of people that are smart, and there's a whole lot of other people that just want to sit around and play video games all day long. And
That's right.
It's being driven by that handful of smart people, but there still have been a lot of them.
Yeah.
Over the last years.
What you got to do is you got to leverage the whole incentive structure so that the people who just want to play video games, you're able to con them into doing something that like might be useful, sort of. I mean, didn't work on me. Okay, I'm trying to design a gravitational wave detector that's not going to like measure anything until the second version of it 50 years from now, but it's fine.
But you have to have that. You just have to start somewhere. The things that we do now, it may an impact 50 years from now. That's okay.
Is it what was it? Titan Uranus? Is it Titan Uranus enough to get you motivated to do something?
Y'all are killing me. So if you guys enjoyed this show as much as I did, because I can't breathe anymore and I'm like tears have been coming out of my eyes, then make sure that you support us. You can support us in simple ways, like you can click like and subscribe and share and hit the notification bell, all those cool things. If you'd like to do something a little bit more, you can join our Patreon. We are in the process of becoming a 501c3 organization, and that takes money. So I want to thank our current patrons, which is Erica Zoles, Ryan, Deneen Murphy, Dan D, Michael Wiseman, Kathy Cotton, Cindy Plaza, me, Aaron Colson, Phil Calderon, Amanda McLeod, and Logan Fisher. I want to thank you guys so much. Every little bit helps, so consider doing that. I also want to talk to you about our other shows, and I have some great things to talk about. So Saturday, we have The Global Atheist, and this week it features Dean and I think it's either Tertia or Tercia, and they're discussing atheist activism. Following TGA, I'll be hosting Women Atheists Unload with Mary Byler. She's an activist and author of Amish Misfit, and she was recently featured on Soft White Underbelly. So if you haven't seen that interview, you've got to check it out because it was amazing. And then on Sunday, we have our Collins show. This week, Let's Talk will be hosted by Apostasy and Neil, the 604 Atheist, discussing epistemology. So be sure and check it out and call in with your questions and comments for these great hosts. We have something for everybody. So, in the meantime, until next time, which will be right around the corner, remember to always think critically. Good night, everybody.
If our being knows this is where we came from, we long to return. And we can, because the cosmos is also within us. We're made of star stuff. We are a way for the cosmos to know itself.
If we are not able to ask skeptical questions, to interrogate those who tell us that something is true, to be skeptical of those in authority, then we're up for grabs for the next charlatan political